Welcome back. So in this video, we're going to look at the calculations involved in our inverse dynamic analysis. Here's a possible research question we might ask, and we'll use this just as a simple example to explore these equations. In fact, this is the same example that we use in the textbook. So if you're interested in the gory details, I'll refer you there. Spend a little bit of time, read through it, think through it, make sure you can compute all of these equations yourself. So here's our research question. What are the sagittal plane moments about the ankle, knee, and hip during a maximum height jump? So we're going to bring someone into the lab and collect some data and ask them to jump as high as they can. What data are we collecting? Well, we see a force plate down here. We'll collect ground reaction forces. We'll talk about what happens in the event that we don't have ground reaction forces. There are motion capture sensors at the hip, the knee, the ankle, and on the shoe here. We can tell these are active sensors actually because there's a little wire coming out of these cartoon boxes. And there's some EMG data as well. We might use those data in Chapter 9 to validate the results we get from a muscle force estimation. So here's some data we might get from an experiment. We'll get joint angles, angular velocities, angular accelerations, and ground reaction forces. And we'll talk about what happens if we don't have ground reaction forces. Along the top is a little cartoon sketch of what the person's doing. So they'll crouch down a bit, and then over here on the right is the takeoff point. And in fact, if we were doing a simulation, we wouldn't need to simulate beyond the takeoff point. At that time, it's just a projectile motion problem. In the plots, we see the angular displacements and angular velocities of the foot, the shank, the thigh, and the trunk. And we'll use these data with our model to calculate the net joint forces and moments. And here's the model we're going to use. So we have 4 body segments. We have a foot, a shank, a thigh, and a hat. HATs for head, arms, and trunk, or head, arms, and torso. We usually just call it the hat segment. And we have some model parameters that we would need to either measure or estimate. We might estimate from cadaveric studies, there are anthropometric tables, and various other ways of getting data for our model. What data do we need? Well, we need masses for our body segments, inertias for these body segments as well, and some measurements. So for example, L1, we have the distance between the ankle and the knee. R2, this is the distance between the knee and the center of mass of the thigh body segment, etc. So assuming we have data from our experiment, we have appropriate parameters for our model, now we can do our calculations. And this is what you might get if you performed an inverse dynamic analysis at each point in time. On the vertical axis, we have joint moments. On the horizontal axis is the time before takeoff. So here they're crouching down, and at 0, they've left the ground. So we'd perform this analysis at each point in time. And for instance, we see that the hip peaks before the ankle. This is very similar to what you'd see in a baseball pitch, in fact. You would see a peak in the shoulder before you'd see a flick of the wrist at the end before the ball is released. And so we're going to walk through some stages of how we would generate these data. So before looking at the specific equations for our model, let's look at the 3 steps we need to repeat for every body segment in the model. As I said, there are 3. The first step is to create a free body diagram. That involves drawing the body segment in isolation from the rest of the universe. We'll draw in the reaction forces and moments and the distance forces and moments, or essentially all the other forces and moments in the system. These distance forces would be like gravity, spring forces, things like that. Then we'll form the motion equations. We'll compute the velocities and accelerations by differentiating expressions for the positions. And finally, we'll apply Newton's second law. For forces, that's F equals ma, or the sum of the forces in the x direction equals m times the acceleration in the x direction. Similarly for the y direction. And similarly, in the rotational domain, we have the analogous equation, sum of the moments equals the inertia times theta double dot. And notice that we don't have the other term. If you look in the textbook, there's an extra term there in equation 8.6. We don't have that term there. In this case, we're always going to be taking moments about the center of mass. So we have this simplified version of the equation. Let's look at our picture over here. So we have our free body diagram. Here's our blue body. We have a center of mass up there. The reaction forces and moments are drawn at the bottom, Fx, Fy, and torque T. we've drawn fx, fy, and t all in the positive direction. We'll note later on, but the sense of these arrows is very important. We have to be consistent. In terms of other forces and moments, we have mg, the weight, or the force due to gravity, acting at the center of mass. And we'll assume that we know some geometry and kinematics. So we have this distance r, and we have this angle theta, the angle of the body relative to ground. Let me remind you of the model we're going to use. We're assuming we have a planar system, 3 degrees of freedom. We're assuming that the foot is rigidly attached to the ground. And so our 3 degrees of freedom are the angle of the ankle relative to horizontal, the angle of the knee relative to horizontal, and the angle of the hip, again, relative to horizontal. So we'll assume we know these angles and their derivatives. We have lengths, L1, L2, R1, R2, R3. We'll assume we have these measurements somehow, either by measuring from our subject or estimating somehow. We'll need masses and inertias for each of our body segments. And as I said before, we'll assume the foot remains on the ground. We can assume it's massless as well. All right, let's start off looking at the equations at the foot. So we'll work our way up. Step 1 is to create a free body diagram. So we have our blue foot in the bottom right corner here. And we'll draw in the reaction forces and moments. Where do we have reaction forces? Well, there's a ground reaction force. Let's assume that it acts at the toe. Not a bad assumption if you're going to be taking off the ground for a jump. Fxg, Fyg. So these are the two components in the sagittal plane of the ground reaction force. I'm drawing them in the positive direction. Doesn't really matter the sense as long as you get the sign right when you substitute numbers in. The other reaction forces, and indeed a reaction moment, will occur at the ankle. And in this case, I'm going to draw them in the negative direction. So here we have Fx1. This is the reaction force at the ankle in the x direction. In fact, that's the negative x direction. We'll draw Fy1 pointed in the negative y direction. And the reaction moment we'll draw in the negative z sense. The reason I'm drawing these in a negative sense is when we do the free body diagram for the shank body segment, we'll use the same variables, but draw the arrows in the opposite direction by Newton's third law. Now, it doesn't matter which direction you choose. We just need to be consistent with all the free body diagrams in our system. So there we go. There's the same thing, a little bit cleaner. We have a complete free body diagram. And now we'll apply Newton's second law to compute forces and moments. So I want you to take a couple seconds here and see if you can come up with these equations on your own. Okay, so we're back. Hopefully you had some success. And let's take a look at the equations together. So for forces, we'll have first the sum of the forces in the x direction. What will they be? Well, let's take a look at our free body diagram. We have Fxg in the positive direction. We have Fx1 in the negative direction. So we'll use the negative sign in front of that term. This equals ma, mass of the foot, times the acceleration of the foot in the x direction. We're assuming the foot has no mass. We're assuming also it has no acceleration. So this is definitely 0. Sum of the forces equals 0. Sum of the forces in the y direction, we have Fyg minus Fy1. Again, this equals 0. And for moments, I'll pick the positive z direction as the positive direction when we compute the sum. So the sum of the moments equals what? Now we need to decide about which point we're going to take moments. We could take moments about any point. The foot has no mass, so we could concentrate the 0 mass at any point we choose. But we'll pick the ankle as the point about which we take moments, simply because Fx1 and Fy1 will not have a contribution when we compute moments about that point. We'll see when we write out the equations why this is convenient. So the sum of the moments about the ankle, we have a contribution from Fxg times the moment arm, which is this distance here, labeled as h. We have a contribution from fyg in the opposite direction, so negative fyg times L. And finally, negative T1, and this, again, equals 0. No mass, no inertia, no acceleration. Right-hand side is 0. So now let's write these equations in matrix form. Our unknowns, assuming we have ground reaction forces, the only unknowns will be Fx1, Fy1, and T1. And let's fill in the blanks here. We have from the first equation, Fx1 equals Fxg. From the second equation, Fy1 equals Fyg. And from the last equation, we have T1 equals Fxgh minus Fyg times L. Is this system solvable? Well, we have 3 equations. As long as we know Fxg and Fyg, then we have only 3 unknowns and we can solve this system. If we did not collect ground reaction forces, then Fxg and Fyg are also unknowns. So we need some more information to solve the system. And we'll come back to this idea once we get to the hat body segment. Okay, so we've finished with the foot. Let's move on to the next body segment, the shank. Okay, so we'll walk through the same 3 steps as we had before. We'll start off by creating a free body diagram, and we'll draw in all the arrows. So here we have the shank body segment drawn in blue with the center of mass shown. And you'll notice one thing here, that the shank is drawn in the first quadrant so that angle θ1 is an acute angle. I always draw free body diagrams like this if I can. It doesn't matter where we draw the body and what angle we make with the horizontal. I find it convenient if I draw them all in this quadrant. So let's draw in the reaction forces and moments. We have a reaction force and moment at the ankle and also at the knee. Based on the convention we used on our foot free body diagram, we have Fx1, Fy1, and T1 like this at the ankle. Notice here I've drawn them all in the positive sense. These are the same variables I used on the previous free body diagram, but due to Newton's third law, we'll draw the arrows in the opposite direction here. We'll use the same convention at the knee. So here, this is the more distal body. So for the more distal body, we'll draw these in the negative direction. So we have Fx2 in the negative x direction, Fy2 in the negative y direction, and T2 in the negative z direction. Finally, we have one other force. We have the force due to gravity pointed downward, m1g. Okay, let's move on to step 2. We're going to form the kinematic equations. In particular, we'll compute the positions, velocities, and accelerations of the center of mass in the x and y directions. So look at the little picture in the bottom right corner there. We'll assume that the ankle is the origin of our global reference frame. So we'll make all of our measurements relative to that point, which means that the center of mass here will be r1 cosine θ1 in the x direction and r1 sine θ1 in the y direction. So we have x1, the x coordinate of the center of mass, is r1 times cosine θ1, y1 equals r1 sine θ1. And we can take derivatives of these expressions to find the velocities and accelerations. Let's do that for the expression for x1. x1 dot, and let's be really explicit here, x1 dot would equal r1 dot cosine θ1. Derivative of sine is cosine, derivative of cosine is negative sine, so we have minus r1 sine θ1 times θ1 dot. We know that the shank body segment is not changing length. In other words, r1 is a constant, so r1 dot is 0. That means x1 dot is simply negative r1 θ1 dot times sine of θ1. So we can take the derivative again to find the acceleration. Let's do that. x1 double dot equals, now we've already decided that the shank isn't changing length. In other words, r1 dot equals 0. So we'll have just two terms to write down here. r1 theta 1 double dot sine theta 1 minus r1 theta 1 dot squared cosine theta 1. And we can do the same thing for the expression for y1. So you should have gotten these expressions for y1 dot and y1 double dot. Again, these expressions are in the textbook, so take a look there if you're looking for the details. And now let's move on to step 3. We'll apply Newton's second law, and first we'll compute the forces, and then we'll do the moments. So why don't you pause the video here and take a couple minutes, see if you can generate these equations on your own. So we're back. Hopefully you were able to do that. You should have gotten these expressions. It's exactly the same procedure as we had before. We'll sum the forces in x. We'll sum the forces in y. On the right sides of these equations, once again, we have ma. In this case, the acceleration is not 0, so we'll need the expressions we derived on the previous slide for x1 double dot and y1 double dot. And now we can add these expressions to our system of equations, written here for the forces only. So assuming we had measured the ground reaction forces, we would know what Fx1 is and Fy1. So the only unknowns here would be Fx2 and Fy2. We'll do the same thing for the moments, again following the same procedure as before. We have a little bit more information in our picture down here because we have forces acting at the ankle and at the knee. And all of these forces are going to generate moments about the center of mass. But it's not too much more complicated. We follow the same procedure, sum the moments about the center of mass, and set that equal to the inertia times theta 1 double dot. And we'll add that equation to our system. Now, once again, if we had measured the ground reaction forces, we would know Fx1, Fy1, T1. So the only unknowns here would be Fx2, Fy2, and T2. We would have 3 equations, 3 unknowns, and we could solve for the reaction forces at the knee. All right, so let's move on to the next body segment. It's the thigh. All the same procedure as we saw before. So if you want the details, you can look in the textbook. We're just going to flip through these really quickly, and we'll see how our system of equations grows. First step is to create the free body diagram. Again, we've drawn it here in blue. We'll add in the forces and moments. Here's the geometry we need. We'll compute the positions, velocities, and accelerations in the x and y directions for our center of mass. You should get these expressions here. You can check your work, maybe work on it yourself. We'll apply Newton's second law. First, to get the forces. Again, the expressions are getting a little bit longer, but the procedure is no more complicated as what we've seen already. Here are the expressions, F equals ma. We can add these equations to our system. And finally, for moments, we'll do what we did before. Sum of the moments equals I2 theta 2 double dot in this case. And we'll append that equation into our system. So now look at our system here. We have 6 equations. That vector has 9 terms in it, 9 variables. But if we had measured the ground reaction forces, we would have been able to compute Fx1, Fy1, and T1. So in fact, we would have only 6 unknowns in this system of 6 equations. So we would be all set to compute the reaction forces and moment at the hip. So in fact, if we had measured ground reaction forces, we'd be done here. If we did not, we need some more information to solve this system. So we can move on to the last body segment in our model, the hat, or head, arms, and torso, or trunk. Once again, we have the same 3 steps as before. Create the free body diagram as shown here. Here are the forces, and there's a reaction moment. Here's the geometry. Once again, getting a little bit more complicated, but the procedure is all the same. Here are the expressions for the position of the center of mass. In step 3, we'll apply Newton's second law. Here are the force equations. We can add these to our system. And finally, for moments, here's the expression, and add that to our system. Now we have 9 equations, and we would have 9 unknowns if we hadn't measured ground reaction forces, so we could solve this system. Ideally, we would have the ground reaction forces. Usually, for example, we get very precise ground reaction forces in comparison to the precision of, for instance, measuring the center of mass of the torso. Nevertheless, even if we didn't have ground reaction forces, we would be able to solve this inverse dynamic analysis. We can repeat the procedure at every point in time, and we saw this plot before. We would end up with joint moments over the entire trajectory of the motion. So to recap, we started off with a motivating example, and we asked, what is a joint moment? We saw that all the biological forces are collapsed into an equivalent net force in the x and y direction and net joint moment. In Chapter 9, we'll do that in the reverse order. We'll decompose that and estimate the forces from the muscles. Finally, we walk through the solution procedure. So in the next video, we'll jump into Chapter 9. I'll see you there.